Welcome back. This is part 2 of the tutorial on Raman spectroscopy. In part 1, we reviewed the fundamental principle and the main equation and information that we need to understand what's going on. So basically, we found that what matters in order for a vibrational mode to be Raman active is for the derivative of the polarizability tensor chi here to be non-zero. We discussed in particular that we can use the character table that describe the symmetry of the material that we're looking at, or the molecule we are looking at, to see which mode, if we know its irreducible representation, is Raman active. And we are going to see another example of that today. I also insisted a little bit on this business of polarization of light, both incoming and outgoing. So the polarization is the direction of the electric field, which is always in a plane perpendicular to the direction of propagation of light. So it turns out that because we are working with tensors, so the tensor alpha, which is the Raman tensor, the particular direction that we are going to consider for the incoming polarization and the outgoing polarization will matter about which actual mode will be visible in the Raman spectrum. So this is a summary, and we are going to discuss application of that in the next hour or so. So let's talk about applications. The first one I'd like to talk to is phosphorene, because it's an interesting one in terms of being a non-isotropic system, and it will allow us to understand a little bit more about this business about the polarizability tensor. So phosphorene is a 2D material. It can have multi-layer. For example, in the schematic that I have on the top right, there are 2 layers, and the schematic on the bottom right is seen from the top. And you can see that the X and Y direction, so the vertical and the horizontal directions, are not equivalent. So it is not an isotropic material. It's a material that has been studied for a little bit less than a decade. It has a lot of interest because of its properties, but in terms of application, it's a little bit more complicated to use than other materials because it easily oxidizes. So it's not very stable in a normal environment. So the first thing that we do when we have a crystal like this is to look at the symmetry. It turns out the symmetry for this material is Cmce, it's a space group. So of course, I invite you to look at resources about space group if you're not familiar with it. But what actually matters is not so much the space group, but is the point group that's associated with the space group. And the point group is MMM. So, by the way, if you want to find these things, there are different libraries that exist, computational libraries, but also websites where we have all the character tables and all the properties and the type of symmetries. So it turns out that for this particular group, MMM, which is also called D2H, depending on the convention we use, we can find a character table. And the character table is actually pretty rich. It's a little bit richer than the example I showed for ethanol in the previous, in the first part of this tutorial. So you see you have number of irreducible representation that are shown on the first column, so AG, B1G, and so on and so forth. And as I mentioned to you, the mode that we expect to be Raman active by symmetry are those that have a quadratic, that behave like quadratic functions. So in other words, only the first 4 modes could be potentially Raman active. The other ones are not Raman active. So there is no way that we will see a peak that corresponds to the AU, B1U, B2U, B3U. And the reason for that is because for those particular vibrational modes that have those irreducible representation, they do not, by symmetry, correspond to a change in polarizability. And as you know, the change of polarizability is really what makes up the Raman tensor. So this is a typical spectrum. Actually, it's not a spectrum. This is the phonon band structure. It's a little bit complicated. We are not going to worry too much about it because remember, as I mentioned at the end of last screencast, because of if we look only at one phonon process, we need to have a negligible transfer of momentum. In other words, only those vibrations that have zero momentum will participate in the first order Raman spectroscopy. So sometimes you do have the second order Raman spectroscopy that I'm not going to discuss too much in this screencast. Maybe that's going to be for future screencast. In those we have more than one phonon involved, and therefore we go away from the zone center. So the gamma point, which is 0, 0, 0, is actually called also the zone center. So we have these different those different modes that we have, and just as a reminder, those modes that goes to 0 at the gamma are called the acoustic mode, and all the other ones are optical modes. And the optical modes are those that have a chance to be Raman active. Okay, so in fact, if we look in details, the B1U and B2U are infrared active. Those modes here are Raman active, but they are not seen in backscattering. I'm going to explain to you what we mean by backscattering, and those modes are typically seen in a backscattering. So backscattering is when when light shines just normal to the surface of phosphorene. So this is not a typo. Ki is 0, 1, 0, so it's along the y directions. This is one of those things about convention, about symmetry groups. It turns out that phosphorene, the space group in which phosphorene belongs, is the y-axis is the axis that's perpendicular to the surface. So if you have a material that's if you have a Raman measurement where the light comes perpendicular, so normal to the surface, those three modes that I showed in blue will not be Raman active. And I'm actually going to show you why this is so. So you could actually see them in Raman, but then you would have to use a different Ki. So we can calculate, in fact, the tensors, the tensor just based on symmetry. And the mode AG, B1G, B2G, and B3G, which basically involve all those modes that I highlighted, but the red one, all those can be calculated by symmetry. And again, because we do have a non-isotropic material, we see that we have a non-trivial, we don't have trivial Raman tensor. So the Raman tensor here are written as R. I'm going to go and describe this in a little bit more detail, in the future, in a few minutes. So the mode that we see in backscattering, again, so those modes that I said are when we have backscattering means that the light is actually shining perpendicular to the surface, are those three modes, A1G, B2G, and AG2, and they are actually seen in Raman shift, and you see here that the frequencies are around 500 wave numbers. This is an example here that was done, a work that was in collaboration with Shear-like, who is now at, I believe she's in Virginia Tech, and she was able to measure those modes at different places of the flakes. So this is not actually great to see the number of layers, simply because the interaction between the layers does not reflect much into the vibrations. So these are the three modes that we see, and we can again show the mode with arrows. So we did this through DFT calculations, and we see how they work. So let's go back into all the modes that should be Raman active, but that we don't see. Okay. So this is a summary again that what I showed you before, and I think it's an important example to understand polarization effect. So again, imagine that we are going to study this in detail now. So imagine that you have your sample here, which is shown by the blue bar, the blue rectangle, and the y-axis is perpendicular to the surface. Now we have, if we're in backscattering, the incident light is perpendicular to the surface, and the polarization is somewhere, so the direction of the electric field is somewhere in a plane perpendicular to the gray arrow, and so it's an angle theta. The scattered light, if we also collect the light that's actually reflected also perpendicular, the polarization of the scattered light will be somewhere in the green plane, the green circle, and the polarization will be given by gamma. Okay, so this is all we need to know. Those four Raman tensor I show there, I'm not calculating them. I did not calculate them, but we can calculate them and obtain the values using also the DFT calculation, for example. However, the non-zero terms, which are those that are shown with letter A, B, C, D, E, F, those numbers, we know that the non-zero, where the non-zero terms are by the group theory. Of course, it could be zero even with group theory, but by symmetry, those should be non-zero. Okay, now let's have a look at the equation on the top right. The equation on the top right is an equation I've shown a number of times. Now let's apply it to this particular case. So remember, GS is the scattered light, GI is the incoming light. Again, this is the direction of the electric field. And you see here that indeed the dot product is obtained. I wrote it explicitly on the bottom of this slide. So again, this is a good place maybe to pause the playing of this screencast so that you can maybe convince yourself. But these vector, the first vector, the vector with the three component there, the first vector cosine theta minus phi and so on, is that corresponds to GS. And you will notice that in this case we have we actually look at the angle with respect to the rotation of the sample with respect to y. And similarly, we can actually calculate the vector for the incoming light. Okay, now depending on the value of alpha, we are going to see what this number means. So let's have a look at those two modes, the B1G and B3G, which I told you are not seen in backscattering. Well, it's actually very easy to see that if you actually used one of the two alphas that I showed there, the alpha for B1G or B3G, the product that I showed on the bottom is indeed zero. So again, a good place to stop and to convince yourself that this product is always zero. So it doesn't matter what you do here, you will never see those two modes in backscattering. If you want to see them, you are going to have to impinge the light at an angle with respect to the sample, and it is indeed doable. The reason why we do backscattering is because this is usually the one that gives the higher signal in most material. So this is, in this case, the example I show here is the Raman tensor for B1G. We can do this for the three modes that are actually Raman, that we see in Raman even in backscattering, and the same exercise. In this case, I wrote the tensor for AG, and we calculate this product, and we find then the intensity for AG depend on the element element A and C, but also on the angle theta minus phi. So this is actually very interesting because when you do this calculation as a polarized Raman spectroscopy, which means that you replace theta versus phi, and here we put gamma equals 0, you can actually obtain, we use gamma equal theta, sorry. We can actually obtain a plot as a function of alpha, and the particular shape will obey a specific function of the angle, as the one I show here. And if you can do that experimentally, this is an additional demonstration that you have identified the right mode. Now I want to move to one-dimensional carbon, which is a little bit simpler. In fact, one-dimensional carbon would be like particularly those nanoribbons that I'm going to talk about. These are small ribbons of graphene with hydrogen on the side. Now, it's difficult it's used to be very difficult to get those very cleanly. You would think that cutting a piece of graphene into ribbons would work, but that's mostly work in theoretical calculation. Experimentally, it's not easy to do. And until about 2010, was the work of the group of Roman Fasel and Klaus Mühlen, there was a new technique that was obtained to, in fact, synthesize those ribbons directly from precursors. And if your precursors are very high quality, you end up with perfect nanoribbon. So there were more work to actually change the precursor so that you have different type of nanoribbon. And this is actually very nice for demonstration of Raman, because now the structure you have is essentially no defect. And you can exactly reproduce, take into account the material with the position of the atoms experimentally and theoretically, and make a match between the two. So that's actually very interesting. So you may wonder, How do we know that we have a ribbon if we do not look at it? So here these are STM images, and actually on the bottom right it's a non-contact AFM image. But imagine that you do not want to do that. You want to do something cheaper and faster. How do you know that you have a ribbon? Well, it turns out there are a number of modes in the nanoribbon, but in particular, there is one mode that's specific to a ribbon of a given width, which is called the breathing mode. So the breathing mode looks like this. It looks like like an accordion breathing. I mean, it's like expanding, retracting, extending, extracting. And you see here that this is indeed a collective motion. And this motion, in fact, leads to a change in polarizability of the material and therefore is Raman active. So these are works that have been done for a while. In fact, theoretically, they were studied well before they were obtained experimentally. In fact, I like to show this work since I was involved in it, especially, I mean, the work was done by van der Schuren, and that's a work that I did in 2008. And that was one of the latest work I did with my PhD advisor, Professor Lambin, which is the person I learned most about my solid state physics with. So what this early calculation showed is the frequency. There is a frequency which is called the breathing mode, and the breathing mode looks like this on the little movie on the left-hand side. That particular mode is Raman active because it leads to change in polarizability, and its frequency is inversely proportional to the width of the material. And this was something that was obtained in 2008, well before those measurements could be made. And a few years later, the measurements indeed showed that when you have those very clean AGNR, so graphene nanoribbon with an armchair edge, 9 means it corresponds to the width, you find that indeed there is a mode around 312 on the experimental data and reproduced by DFT in the dashed data that correspond to the radial breathing mode, and it's very specific to the width. So it's a powerful technique to know the presence of a very specific type of GNR. So these were reproduced the same year by Klaus Mullen in different type of GNR, 5, 10, 15, and 28 GNR with those radial breathing mode. And if you put them all together on a graph like this, and with the theory work from van der Schuren, you see that all those measurements fit very nicely on the curve, which means that it's a predictor for the type of AGNR that you have. So which is very nice. More work was done in the group from Anping Lee in Oak Ridge National Lab, work that we collaborated on. But there, not only they found for 7, 14, and 28 GNR, but actually they found another mode, which is a lower frequency mode, a very small peak, which is called a Shear-like mode. And I'd like to talk to you a little bit about that peak. So this is the result that was obtained by Anping and in the group of Anping. And if you zoom on the low frequency, you see there is a shear mode around 262 wave numbers. I'm going to show you what the shear mode looks like in the next slide. So these are the different breathing-like mode for graphene nanoribbon with an armchair type edge of 9, 7, and 5. So you see the breathing mode look like this. For the shear mode, the motion is actually a shear-like motion that you see here. And these motions actually also correspond to a change in polarizability. However, they are much less active than the breathing-like mode. So the shear mode are not always easy to find. They were found by this work again in the group in collaboration with a group of Roman Fazel, where shear-like mode were obtained for 3 other type of AGNR, and could explain all of them using again density functional theory. And if you go back to the figure obtained from the Ma and Al paper, so for the Oak Ridge group, you see that those value actually fit perfectly well on those lines. You can also look at more complicated geometries because, of course, depending on the precursor you use for assembling GNR, you obtain different type of geometries. So this is one of them, for example, and you have different modes. This one is actually Raman active. This is an example here from, again, the group of EMPA and under the leadership of Oliver Groening. And this particular type of GNR, they have complex edges, actually have topological properties. We're not going to talk about that here, but the point is that it's important to have very clean and very defect-free GNR of this type. And when you look at that, you can obtain experimental data at different times, 0 days and 5 days, to show that they are stable. And all those modes can be reproduced by density functional theory. It's the bottom graph, and that allow us to know for sure that we have this type of GNR in the material. So this is yet another example here of another material that's not clean edges again. And one more time, the experimental data can be understood theoretically, showing that we indeed have the material that we claim to have. Now let's go back to vibrations in two-dimensional materials. At the beginning of this screencast, we spoke about phosphorene. Now I'm going to focus on other 2D materials and try to go a little bit more in depth about the different type of frequencies we can have and how Raman can be used. So the material of choice currently and materials of interest is MX2, so metal dichalcogenide. So M is a metal and X is a chalcogenide. An example of which is molybdenum disulfide. You have a little representation of the crystal shown in the middle of this slide. If you look at the different frequencies of vibrational frequency of that material, you can again classify them using the irreducible reproduction related to the point group. And as we know from what I explained in the first part of this tutorial, we can know which one of those modes are Raman active. It turns out the Raman active ones are shown schematically on the left-hand side. And the intensity, again, just to remind you, it's an important point, is that we have Raman activity if the derivative of the tensor, polarizability tensor chi is non-zero, and that will only happen for some symmetry. So you have different type of dichalcogenide. So here I'm just showing you two examples, MOTE2 and MOS2. And indeed, you can see those modes in the Raman mode. In fact, in MOTE2, you see all three modes: E2G, A1G, and B2G. While in MOS2, they are ordered differently, and in fact, B2G is not really visible. But the point is that these modes are well defined, and the frequency changes. Slightly with the number of layers you have in the material. So Raman here can be used not only to know the number of layers, but also the quality of the material and how much of it we have. So that's very interesting. Before we move on, I would like to explain to you a little bit of difficulty for these materials that's actually come from convention. I mentioned to you that the mode are always labeled using the irreducible reproduction of the point group. However, in the case of MX2, there is a little bit of a lack of clarity, which I would like to address in one slide. That was work done by Humberto Terrones, a former colleague of mine at Rensselaer Polytechnic Institute, and he explained this very well in this paper. So basically, this MX2 material, and I'm showing you here a side view of a 4-layer MOS2, for example, and as well as the top view. These materials have been known in a bulk form, so essentially an infinite number of layers, for many years. The thing is, the symmetry, as I told you, symmetry is very important for Raman activity. The symmetry of the bulk material is slightly different from the symmetry of a single layer or a double layer. In fact, of odd number of layers and even number of layers. So the symmetry can be, for the bulk, is found to be the MMC or P63 MMC symmetry, for the odd number of layers P6M2, and for the even number of layers P3M1. In fact, this is actually a very interesting exercise to see the presence of different types of symmetries depending on the number of layers that we have. But the point is that those groups correspond to different point groups, and therefore we do anticipate that the irreducible representation are going to be different from those three groups. And this is actually something that's interesting to explain. These are the three character table. It's a lot of data, but I highlighted those modes that are Raman active. Again, these are those that have quadratic functions in the column. And you see for the bulk, which is at the top, we have three modes, A1G, E1G, and E2G, as I explained before. Now, for single and double layer, or any finite number of layers, we see that the names are slightly different. Okay, we see that the names are different. We are talking about A prime mode, E prime mode, and E prime prime. So in particular, we should really use the A prime 1 or E prime for a finite number of even layers. But very often in the literature, you will see that authors use actually the naming of the bulk. So it can be surprising that if you have a crystal which has a D3H point group, that you would report Raman modes using A1G, E1G, or E2G, even though those irreducible representation do not exist in those materials. So I just like to show you that sometimes scientists add difficulties to what they do and make it difficult sometimes to read, but this is the way it's done. So this is basically how we can calculate these things, the irreducible representations. So I just want to show you this. It's just so it's clear that even though the rules should be pretty clear about which labels to use, well, scientists being humans, sometimes they do not follow the rules exactly. Anyway, the point is that if you look at all the Raman active mode in transition metal dichalcogenides, that's what TMDC means, you see that you have a number of modes, and all of them, of course, are part of those A1G and E2G and B2G modes. As you see, I highlighted again in blue the modes that are not Raman active. Those modes are actually infrared active. We do not see them in Raman. Actually, no, we see those in Raman. I'm sorry, this B1U is not Raman active. Sorry, but the modes are going to be the activity of the mode are going to be different depending on how many layers you have. For example, so FL stands for few layers. There are some modes that are not active in the bulk, but that will be active in the few layers just because of symmetry. So again, it would require a little bit of study. There's quite a number of papers over the past few years explaining this. But the take-home message of this slide is that an analysis of the symmetry usually suffices to understand what's happening and what you measure, without even doing any calculation to start with. So those modes are very interesting. It's just not just to know that the material is there, but also, and I also mentioned, to see how many layers you have. But another work that we've done, and I think it's quite remarkable because it shows really the power of Raman in those two-dimensional material, is understanding the defect generation in those material. So sorry, I skipped this one. Okay, so TEM is transmission electron microscopy, which is a technique where you essentially interrogate the material with a fast electron beam. Okay, and it's usually a scanning stem and a scanning probe, and then you end up with an image, with a TEM image. Okay, so what we were interested in this work in 2018 is to understand the defect formation. And then people have been looking at this. So for example, the group of COMSA has been looking at the defect generation, so single vacancy, single sulfur vacancy, and they were able to measure that experimentally on the TEM image. They look like those little tripod. In 2016, we decided to try to see if we could use Raman to understand the number of defects instead of having to count the number of defects. So again, Raman is much cheaper to use and faster and cheaper to use than aberration-corrected transmission electron microscopy. So what we did there, we look at the effect of vacancies on the mode that we have, on the A2G and A1G mode. So these are the two visible modes for MOS2 in the high frequency range. And what we found by doing the calculations is that one of the two modes, so here we actually have both names, but the proper name is A1 prime and E prime, in fact, as I explained from a symmetry standpoint, symmetry perspective.
we see that the E prime mode is actually quite affected by the number of defects, of vacancies, while the A1 prime mode are not. So experimentally, the group of Derndic at University of Pennsylvania, they devised ways to actually measure the Raman shift, but most importantly, to find an independent way to calculate, to know the number of sulfur vacancies that you have in the material. And so therefore we're able to plot this. And so in this joint work in 2016, we're able to show that indeed the monitoring the shift in the Raman mode is enough to explain how many defects you have. So confirming the theory, but also showing that there is a strong correlation between sulfur vacancies and the shift in the mode. So that's very, very good. You can also do other things in Raman. For example, you can do isotope doping, isotope engineering. In that case, you can replace natural molybdenum with one of these isotopes, like for example, moly 100 or the moly 92. And in that case, it turns out that you see that the peaks actually shift. They shift according to a simple spring model, in fact. And you see, for instance, that the E1, the E2G mode shifts as a function of frequency. The higher the mass, the lower the frequency. And so you can measure that. What's interesting in this work is that you see that the A1G mode does not change so much. And this is because in the A1G mode, and you see the schematic with the arrows, the molybdenum atom does not actually move. It's actually the sulfur atom that moves. So of course it doesn't change the frequency. So you see, you can really use classical physics, like I would say freshman physics, to understand many of those things. So it's very interesting. Okay, I would like to move to another topic, which is NanoRaman. Again, this is a work that was done in collaboration, in this case with the group of Ado Giorio in Brazil. And for that, I'm going to explain I will use a typical example to explain what we've done here. And what we're interested in is graphene. And in fact, a graphene here is on top of another graphene. And the idea is that we call the twistronics. So twistronics is the idea that one of the layers is twisted compared to the other one. And if you look at this movie, you see that you form superstructures. I call moire superstructure, like for example here. So a structure that has a periodicity that's actually larger than the periodicity of graphene itself. Looks a little bit like wallpaper from the 70s, but we are not going to worry too much about that. So many people have worked on this. It's an extremely active field in low-dimensional solid-state physics and material science. The reason is because of some of those papers that I list on this slide, showing that there is a strong correlation leading, for example, to superconductivity and ferromagnetism in those twisted layers, depending on the layer that you have, depending on the angle that you have. So from my perspective, I was interested in looking with my students about the formation of domain, the relaxation domain in the structure, due to the fact that you do not have aligned registry. So in this work here, which was led by Michael Lemparski during his thesis, he looked at the reconstruction of those domain. The reconstruction is due to the fact that the potential felt and experienced by an atom on one layer changes depending on the twisting. And what we see here is the material attempt to get into the most stable configuration, which is AB stacking. So AB stacking means that an atom is on the top of a center of an hexagon, for example. But of course, it can't do that because of the twist angle. So as a result, the very stable domain of AB stacking or BA stacking, which is equivalent, must be separated topologically by region of AA stacking. So AA is when all the atoms are on top of each other. And as a result, in between those domains, there is a boundaries. So there's a grain boundaries, and these are what we call they actually lead to the presence of solitons. So if we have presence of solitons here, that means that we have very specific vibration in the material that we can expect. So we do that, and that's what we've looked at, and we were interested to know how does that affect Raman. Okay, so this is a typical result that we have, and we indeed find that the structure tries to maximize the AB and BA stacking, but must be and minimize the AA stacking with grain boundaries in between. So that was actually quite nice. Now, we've done a number of calculations on this, but what was interesting is after we did the calculation, we were approached by the group of Ado Jorio, who has, Ado Jorio is one of the big names in Raman spectroscopy in low-dimensional material, and is very interested in the development of this technique here, which is called NanoRaman. In NanoRaman, essentially, the idea is that the Raman signal is maximized by a local increase of the electric field. So as you remember, the electric field plays an important role because it's basically the media through which the material interact with the laser light. And in this case, the idea is to use a tip-enhanced Raman spectroscopy. So that's what TERS means. But the point is, because of the tip effect, you want a very high local electric field. And by scanning the tip across the material, you hope to look at the local Raman response. So that's what the TERS is about, and we call it NanoRaman when we go towards a resolution of about the nanometer scale. So in any case, here is the way the material works. And what was done in this work a couple of years ago, in collaboration with them in this Nature paper in 2021, was to use a tip and look at local Raman response as a function of the position of the tip. And this is what was obtained. You will notice that the resolution is not quite nano; it's probably a few nanometers, but it's actually pretty difficult measurement, so it's actually pretty reasonable, pretty remarkable. And they were able to measure to actually monitor a certain frequency, a certain Raman mode, as a function of distance. So something that's very nice. In this case, the objective was to focus on what's called the G band, which is in around 1600 wave number, as you see on the bottom left. G band is a vibration of an hexagon in graphene, and it's basically the G band tells you that you have graphene essentially, or you have sp2 type bonding. What we did in our group is to calculate the band structure, so the phonon band structure for different twist angle. So that was a difficult calculation done by Michael, and you could see that the presence of the twist led to a shift, to a splitting of the different modes. In particular, if you go to the top left, you see that the G band is actually split there, quite a significant split. And you can look at the different splitting on the Raman activity now in the experimental data here. Now I have to attract your attention to one important aspect, is that experimentally the frequencies are a little bit lower than theoretically because of the model. The model does not is not completely quantitative, but I need to be in all transparency, I have to say that. But the point is, Ado's group was able to measure how that peak, the peak that's the G band, changes with distance. And this is what the top right image shows. And actually is able to also see the different splitting in the band, just like we predicted theoretically. And in fact, theoretically, this is what we obtained. Obtain the different image that actually look remarkably similar to the one that were obtained experimentally. So of course, I wanted to finish this screencast with a discussion on this NanoRaman spectroscopy, because I think it's very important to know that techniques are still being developed, and it's not unlikely that maybe in the future I will do a separate screencast on the NanoRaman if I have time. So this is what concludes this tutorial on Raman. So second part, I hope that you learn a little bit something on Raman. I do understand that it's the first part was very fundamental. The second one was both fundamental and also maybe some advanced topics. Try to do my best to keep a balance between them. So Raman spectroscopy is based on the inelastic scattering. By inelastic, we mean that there is an exchange of energy between light and the vibrational mode of a material. Raman really measures vibrational frequency, but does not measure all of them, just measure those that are symmetry allowed, and we sometimes call that Raman selection rule. Because vibrations are unique signature of a material, Raman will be a unique signature of a material, and I actually showed you even more that Raman can measure structural modifications, strain, defects, and all sort of properties in the material. What's nice about Raman spectroscopy now is that it's inexpensive, it's a non-invasive technique, so it does not modify your material. So your material, once you characterize it with Raman, is not going to be destroyed, and you can use this with a tabletop kind of experiment. I would like to thank you very much for your attention, and I appreciate the fact that you came all the way to the last slide of this presentation. Thank you.